Okay, so now continuing on the solid mechanics. So we have tried to solve some numericals related to Young's modulus, rigidity modulus and all. Okay, so last numerical we are solving was rigidity modulus. Okay, using rigidity modulus, when you are applying a force parallel to a lead kind of slab, when you are applying a force parallel to a lead slab, which is 10 centimeter depth perpendicular to the plane of paper, 10 centimeter depth, but 50 by 50. In this direction, it is 50 by 50. Depth is 10. So the area on which the force is acting is 500 centimeter square. So knowing this, if we are applying a force of 9 into 10 to the power 4 Newton, so we find out what is the shear stress and we know what is the rigidity modulus. It is there given in the table, which is in like in the GPA value it is given. That rigidity modulus was given. So knowing the rigidity modulus, which is G, which is 5.6 GPA or whatever. So knowing this, we know your shear strain is equal to shear stress by rigidity modulus, and shear strain is nothing but your delta x by L. Then we got how much is delta x. So that was our question, by how much the slab is going to be displaced. Yes. Okay, so this is a numerical on this is a numerical on rigidity modulus. Similarly, we have some more numerical on Young's modulus, or you can have some numerical on the bulk modulus and many other things which can come in your CET or any other entrance examination. Okay. So there can be numerical on Young's modulus, there can be numerical on rigidity modulus, there can be numerical on bulk modulus also. Okay. So you can take a picture of it so that we can put it as a reference in future. Okay. So the idea of taking picture is like you don't have to take screenshot from the video that we upload. Instead, we can attach it as a document in the attachment reference section. Okay. So now getting into the next part, some simple numericals on Young's modulus and bulk modulus. So we will solve something on Young's modulus now, which is the related to longitudinal stress and longitudinal strain. Okay. This is in your class 11. This may not come immediately in your 12th exam now, but it will come in your JE or in your CET or those exams. So you should devote some time for class 11 also. Okay. So let us solve some numerical on Young's modulus. Okay. Let us say, this picture I had drawn for solving something related to bulk modulus, but I'll do it later. First, let me quickly do some numerical on Young's modulus. Okay. So the question here is, a structural steel rod has a radius of 10 mm and a length of 1 meter. A 100 kN force stretches it along the length. Calculate the stress and all that. It's very, very simple. Okay, very simple. So this is a rod. This is a rod. You are applying a force. This rod, if you take a cross section from the side, it will be a circular cross section. Okay, so it will be a circular cross section. So here it is given that a F is, so the length of the rod is 1 meter. So this is your length of the rod, which is 1 meter. Okay, so the length of the rod is 1 meter, and you are applying a force F is equal to 100 kilonewton. You are applying a force of 100 kilonewton, which stretches it. So it will get stretched by some this thing. So let the length be 1 meter and let the elongation be del L, which is a unknown now. Let it be del L. Okay. Calculate stress, elongation, and the strain on the rod. So what are the questions? A, stress, how much? B, elongation, how much? C, strain, how much? Okay. So these are your 3 questions. Okay. So it's very straightforward. Okay. So the length. Okay. Young's modulus. Okay. A structural rod has a radius of 10 mm. So this radius R is equal to 10 mm. Okay. That means your D is equal to 20 mm, right?
Yes.
Diameter. Okay. So now you know this, and then Young's modulus. So you are writing Young's modulus as Y here. Okay. So Young's modulus is 2 into 10 to the power 11 Newton per meter square. So now you know everything that is required to solve the problem. Okay, so stress, you write it as
Force
sigma, right? Sigma is equal to force by area. Okay, so you need to be consistent with the unit, that you need to be very careful. All that is important here is units. Okay, so force is 100 kilonewton, that means it is 100 into 10 to the power 3 Newton, right? Which is nothing but 10 to the power 5 Newton. So you have to convert things to the Newton and meter.
Yeah.
Okay. So you have 10 to the power 5 Newton. Then your area. So area is equal to pi by 4 D square. Okay. D is 20 into 10 to the power minus 3
whole square.
meter whole square. Okay. So it becomes pi by 4. 20 whole square is 400. And 10 to the power minus 3 to the power 2 is 10 to the power minus 6. And this is meter square.
Yes.
Clear? So this becomes pi into 100. 400, 100 cancels. 100 into 10 to the power minus 6 meter square. Clear?
Yes.
So your stress become, in place of A you replace 100 into 10 to the power minus 6 meter square. Clear?
Yes.
So this becomes 10 to the power, so this 100 into 10 to the power 6, it becomes 10 to the power minus 4. Right?
10
So,
by 9.
so 10 5 into 10 to the power 4, it will become
10 by
okay.
9.
So divided by pi Newton per meter square. Okay. So this becomes 10 to the power 9. 10 to the power 9 divided by 3.14 MPa, Newton per meter square, is nothing but PA, Pascal, because Newton per meter square is Pascal.
Okay.
Okay. Or you can
10
tell it
power
as 10 to the power 3 megapascal divided by 3.14 megapascal. Clear?
Yes.
So your stress sigma becomes 1000 by 3.14 megapascal. So which will come out to be, so stress, if you solve it, the stress is coming out to be say 3. It will be something around 300 megapascal, in that range. Okay, so 300 megapascal. So
yeah, it will be around 300.
Okay. So now you know the stress. Okay. Now you need to know the elongation, like del L. Okay. So you know the formula for Young's modulus, which is nothing but your stress by strain. Okay. Right.
This by L by del L.
so you have to be very careful with unit here. So stress, you already know that it is 10 to the power 9 Newton per meter square divided by pi.
Yes.
That is your stress,
Yes.
right? Then stress you know. Then strain is
Del
nothing
L
but
we
your
don't
del L by L.
L is 1 meter.
L is 1 meter. So here only thing you want to know is delta L, because Y also you know as 2 to the power
10 power
2
11.
into 10 to the power 11 Newton per meter square.
Yes.
Right. So this you know. Then 10 to the power 9 divided by pi. Okay. So this
By
Newton-
del L. Because L is 1.
So stress and del L by L. Okay. So 10 to the power n by pi. Then this side Newton meter square, this side Newton meter square will get cancelled out. Okay. Then this whole term divided by del L by L. Okay.
Yes.
So you will get del L by L. So you are getting del L by L is equal to 10 to the power 9 divided by pi
divided by 2
whole divided by
2 into 10 power 11.
2 into 10 to the power 11. Okay. So this becomes let us say 10 to the power minus 2. Okay.
By
10 to
2
the power
pi.
minus 2
By 2 pi.
divided by this
2 pi.
2 pi.
6.14.
Okay. So
6.28.
meter. Okay. So 10 to the power minus 2. These are all meter.
6
Okay.
by 6.4.
Length is 1 meter. That's what we have done. So delta L by L is this. So L is 1. Okay. So delta L you just multiply by 1. So 10 to the power minus 2 divided by 6.28 meter. Okay.
Yes.
So this 10 to the power
1 by
2
6.
meter.
1 by 628.
So 1 by 100 meter.
Yeah.
Okay. 1 by 100 meter is 10 mm
10 mm.
or 1 centimeter. Right?
1 by 100.
1 by 100 is
1 by
centimeter.
628 basically.
1 centimeter divided by 6.28. Okay. So something around less than 1 centimeter, like something around 0.1 centimeter or 10 mm. So that's what you are getting del L is equal to something you are getting answer at 1.59 mm. So you can solve it and find out.
You have to convert it to mm after.
Yeah. So that is the second question is your elongation. Then strain is very easy. Strain is you know.
Del L by L.
Y you know. Sigma you know. That is what is the strain.
Direct del L by L.
Yeah.
We
So
found
strain is nothing but sigma by Y. That's all. And it will be unitless. Be careful about strain. It is unitless. So stress you have already found out. This is the value. Okay. And Young's modulus you already know.
We found elongation also. We can do del
No, don't worry about elongation. Stress by strain you know. You want to find strain. Okay, you have got elongation also. So the elongation divided by L also is this. So here you got elongation. Elongation divided by length in mm. You have to convert it to mm by 1000. So 1.59 by 1000.
Yes.
So it will become 0.00159.
Yeah.
Okay. So that will become 0.00159. You can multiply by 100 and convert it into percentage. Okay. So this is one numerical on Young's modulus. We'll do one more. You just take the picture of this and then we'll do one more. Okay. So See, this is my subject. Okay, I am a mechanical and aerospace engineer. So structure, I have been doing structure for so long. So that's why it's very easy. This is the basics, fundamentals. There is nothing, no derivation, no complicated mathematics here. Only remembering the formulas. You are not doing any integration, derivations. Like you are not doing any of those things. Very simple formulas. If we are not able to do these things, then what is the point actually? They are very simple, and we should never like, if you figure out which are the subjects you should solve, like in your JE or in CET, you are targeting that I'll do 60-70% or whatever out of 320. I'll do say 70%, okay, or let us say 60%, 180 marks. So why, which are the selected few 60% topics I should cover? So I would say this is one of the like this solid mechanics is a must. Fluid mechanics is a must. That equation of continuity, Bernoulli's equation, very simple. Then I was telling about whatever I have taught about vector algebra, dot product, cross product. Those are very simple formula driven numericals. Those you should never leave. Write down all the formulas in your white paper and memorize all those. I am not asking you to memorize anything, because you know the concept, it will be easy for you to memorize. First understand the derivation, understand the concept, then memorizing things will be very easy.
Yes.
Okay, so the question is a copper wire of length 2.2 meter. So let us say wire made of copper whose length is 2.2 meter. Okay, meter, and a steel wire of length 1.6 meter. Wire made of steel length is equal to 1.6 meter. Okay, so this is the thing. Both the diameter is D is 3 mm. Okay. So this is my copper wire, this is my steel wire. So this is made of copper. So copper symbol is a formula. Symbol is Cu. Okay, and that wire steel is let us say iron or whatever. Like you can say steel. Okay. So this the diameter of both the wires are same. Okay. The diameter of both the wires are 3 mm. D is equal to 3 mm. Okay. Why we follow mm? Because the dimensions are not
very
in
small.
that is the practical dimensions. Okay. So 3 mm are connected to end. Okay. So they are connected to connected end to end. Okay. They are connected end to end. When stressed by a load, the net elongation is found to be 0.7, obtain the load applied. Okay. So these two wires are connected end to end. Okay. So this is one wire. Okay. Then you are connecting another wire. Okay. So this length, let us say this is copper. Let us say this is steel. Okay. Let us say this is 2.2 meter. Let us say this is 1.6 meter. Let us say diameter is 3 mm. Let us say diameter is 3 mm. Okay. So they are connected end to end, and then you are applying some force. Okay. You are applying some force here. Okay. When stretched by a load, the net elongation is found to be 0.7 mm. So this complete thing has moved by, let us say it has moved, this wire has come to this place. Okay. So this is complete elongation. Delta L is equal to 0.7 mm. Okay. 0.7 mm. Okay. So when you are applying a force, the total elongation is equal to 0.7 mm. Then the question is, obtain the load applied. What is the force? If the elongation is this, what is the force? Okay. So I can do it like this. Say the total elongation delta L is equal to delta L copper plus delta L steel. Right?
Yes.
The force is same force is applied everywhere.
On this. On
Okay,
both.
so this delta L copper is nothing but like we know the formula for delta L. So we know like the Young's modulus is nothing but stress by delta L by L.
Yeah.
Right? So I know my delta L by L is equal to sigma by Young's modulus. Right?
Yes.
So my delta L is equal to sigma by Y into L. So sigma L copper, delta L copper is equal to okay. So delta L copper is equal to sigma by Y copper, right? Because copper Y is different.
Yeah.
Into length copper, right? Length
Yes.
of copper and length of this is different. Okay.
Yes. Yes.
So this I can put. Okay. So delta L is equal to sigma. I know sigma is nothing but force. Force is same on both.
Yeah.
Force by area copper. Okay. Divided by Y copper.
Yeah.
Right. Into L copper.
Length of that.
Length of that copper wire. Plus F by A steel. A steel. Okay. Divided by Y steel.
Steel and L of steel.
Y steel plus length of steel. Okay. So length of steel I know 1.6, length of copper 2.2. Area will be same for both. Area will be pi by 4 d square. Okay. Okay.
Yeah.
So no, you now know everything.
Yes.
You know everything. Only F you do not know. Okay. And you know delta is equal to 0.7.
0.7 mm.
So be careful about the units.
Yes.
So if you want to make it mm, make everything mm. If you want to make it meter,
Meter.
make everything meter. So this is one equation, one unknown.
Yeah.
So you can solve it. So you can find out what is the force. So you can solve it and show it to me actually. How much is the this
Force.
thing? Force.
Okay.
Actually, this is not. Let me see. Actually, what the problem is? Both the diameter are connected end to end. Okay. Both of diameter 3 are connected end to end when stressed by a load. Okay. So the components relation under tension because they have same tension equal to load W and the same area. From equation 9.7 we have stressed Young's modulus. Okay, that is fine. Okay. Total elongation is this. Okay, so we can solve it. Okay, so that's how you can solve it and find it out.
Okay.
So now you can take a picture. So we have done two numericals on Young's modulus. Okay. Then we'll do one on bulk modulus. Okay. Yeah. Okay. So we'll do one on bulk modulus. That's a very interesting numerical on bulk modulus. Just I hope you understand everything,
Yes.
right?
Yes.
Because they are attached end to end and you are applying a force. The same force is applied to both the person. See,
Yes.
two portions are when they are parallel. When two things are in parallel and you are applying a force, the stronger member will take the more force,
Yes.
right? one weak person is there, one strong person is there. You are applying a force. If they are in parallel, more load will get transferred to the stronger one.
Stronger one, yes.
But in case of series, it will go equal force to both.
Both.
Okay. So
Yes.
that's why series. So even in your electrical thing, when two resistors are in parallel, the resistor with higher resistance will take less current. The resistor with less resistance will take more current, because it is it all depends on that. Okay.
On the resistance.
So you know thick conductor. That means its area of cross section is high. That means its resistance is less. If resistance is less, that thick conductor will take more current.
Yes.
That is that's the basic understanding. Okay. So now we will do one numerical on bulk modulus. Okay. So bulk modulus. The question is, the average depth of Indian Ocean is about 3000 meter. Okay. Let me say this is my Indian Ocean and this is some water.
Yes.
Okay. So the depth, average depth. Okay. It can be like this. So you take the average.
Yes.
Okay. So the average depth is 3 kilometer, which is around 3000 meter. Okay. This is the average depth of Indian Ocean. Calculate the fractional compression delta V by V. So we have to find the fractional compression. Like say I was doing, so this is this. So because of pressure, it will get compressed by, something will get compressed by certain amount, right?
Yes.
So this one is V, and this this contraction is, if you measure the volume, it is delta V.
Yes.
Okay, so initial volume is V, final volume is V minus delta V.
Yes.
Okay, so they are asking calculate the fractional compression, which is nothing but delta V by V. Compression is delta V, but what is fractional compression? That is a fraction. So delta V by V is the fractional compression.
Yes.
The question is calculate the fractional compression delta V by V of water at the bottom of the ocean.
Yeah.
Given that the bulk modulus of water is this.
Yeah.
Okay. So the bulk modulus of water. You need to know bulk modulus of water. So here comes the usage of bulk modulus. Okay.
Yes.
So a bulk modulus of water is something 2.2 into 10 to the power 9 or 8. How much it is?
10 per 9.
Okay. So bulk modulus K is 2.2 into 10 to the power 9 Newton per meter square. Okay. So this is what you know. And so suppose he is telling, if you put a sphere or something at the bottom of the Indian Ocean, how much will be the fractional compression of that? Okay. So average depth of Indian Ocean is this. Calculate the fractional compression of water at the bottom of the ocean given the bulk modulus. So fractional compression of not a sphere, like I am telling any water, fractional compression of water they are asking, not any sphere. Otherwise you will have to take the bulk
Volume
modulus
of
of that material.
Understood.
They are giving only water, how much it will be compressed. So that how you will get to know. Okay. So that you can know by, so you know bulk modulus is nothing but your pressure divided by delta V by V. Okay. So you want to know just delta V by V here.
Yeah,
That is the
pressure we
fraction.
know.
So it is pressure by K. Right? K already you know. This is the value. Only if you know the pressure at 3 kilometer depth, then done.
Yes, yes.
So what is the pressure at 3 kilometer depth? I have already taught you in fluid statics. Pressure is equal to rho into G into H.
Rho
Hope
G
you
H.
remember this.
Yes.
Okay. So rho of water is nothing but 1000 kg per meter cube.
Into
9.8 meter per second square.
into 3000 meter.
Into 3000 meter. Okay. So if this is the case, you know your pressure. Okay. So your pressure is equal to 3 into 10 to the power 7. Okay. So 3. So this they have put as 10. Okay. So 33617. So 3 into 10 to the power 7. Newton per meter square. Okay.
Yes.
So your delta V by V is equal to 3 into 10 to the power 7
By
divided by your
dividing
K, which is 2.2
2.2
into 10 to the power 9.
9.
So that fractional compression is coming out
Around
to be
1.5.
0.0136, which is equal to 1.36% if you multiply by 100.
Yeah.
That is the answer. Okay. So you get to know the fractional compression. So this is a numerical related to
Bulk
bulk
modulus.
modulus. So we are done with some numericals related to Young's modulus, rigidity modulus, and bulk modulus.
Yes.
So next we will cover some more things on application of elastic behavior of material. Okay, Poisson's ratio and all we have finished. Elastic energy we have finished. Then application of elastic behavior of materials we will cover in the next session. That will be another 25 minutes. Okay. Okay. Thank you.